In this presentation, we will introduce the idea of what is known as linear regression, which is covered in sections 8.2 and 8.3 of our textbook, as well as sections 8.2 and 8.3 of the alternate textbook that we have been using. In a previous video presentation, we looked at how to display bivariate data using a scatter plot. We also explored criteria for what makes a good linear fit by introducing a new statistic called correlation. Today, we're going to look at how to find and interpret what is known as the line of best fit through a set of scatter plot points. So the so-called linear regression equation, y hat equals m, the slope of the line, times x, the explanatory variable, plus b, the y-intercept, gives the equation of the line that best fits the data that's given in a scatter plot. We will use technology to find the regression line for a given set of bivariate data. Specifically, we will use our guru, as was demonstrated in a prior video assignment that hopefully you completed prior to today. So from section 8.2 and 8.3 of the alternate textbook, let's look at a couple of examples that illustrate what we mean by a line of best fit and a linear regression equation corresponding to it. So here on the screen, you can see on the left, I have a scatter plot of cricket chirps versus temperature. On the right-hand side, I have shown a line of best fit that was generated by our guru going through the points, the line of best fit, and the equation, which we call a linear regression equation, that matches that line is shown on the screen, and it is y equals 4 and 67 thousandths times x minus the y-intercept of 204 and 2/10. In this second example from the alternate textbook, I have graphed a scatter plot of demand data in which I'm graphing the number of items sold versus the price per item. We can see that the scatter plot has a negative linear correlation because it's going downward from left to right. And on the right-hand side, I have again drawn using our guru a line that best goes through those points. That's called a line of best fit. And our guru has generated an equation for that line as part of what it displays. Let me clear up a common misconception that students often have regarding linear regression equations. Many students believe that the linear regression equation should produce the observed value of y for every value of x from the data set. This is not true. For some values of x, the predicted values of y will be far from those observed in the data. A significant correlation does not guarantee that one variable causes a change in the other. We've discussed that before in a previous video. However, we as humans tend to infer such a cause and effect relationship. If we decide to take this risk, there is some conventional structure and terminology that is involved. So for example, we always let x, the horizontal axis, serve as what we call the predictor or explanatory variable. And we let y, the vertical axis, serve as what we call the response variable. Also, it's often called the dependent variable. So let's go through some examples in which we have collected data for each pair of variables that we will look at. We want to make a scatter plot. Which variable would you use as the predictor variable and which as the response variable, and why? What would you expect to see in the scatter plot? Discuss the likely direction, form, and strength. So for the first example, we want to look at the test scores from a set of students, scores from test 2 and scores on a final exam. So I would use as my predictor the scores from test 2 and the response variable being the scores on the final exam. I would expect there to be a positive correlation. In other words, I would expect the scores on the final exam to show some improvement. That may not be the case, so the likely direction would be upwards from left to right. I would expect the strength to be fairly strong, but again, that's open to debate. How about this next one, height and weight? Well, I would expect the height to be a predictor variable, weight to be a response variable. I would expect to see a positive correlation. In other words, as somebody is taller, I would expect them to be heavier. And that's that one. Okay, so the next one, height in inches and height in centimeters. Either one of these could serve as the predictor and either one could be the response variable because the only difference in these two variables are the units. I would expect there to be a perfect positive correlation in this case with the line going upwards from left to right. because all we're doing again is changing the units for height. The last example, shoe size and GPA. You know, I don't think there's any correlation at all between these two things, so you could pick either one as the predictor or response variable. I would expect the scatter plot to show no linear correlation and no direction, form, and strength associated with that particular example of those two variables. Let's now talk about some of the details associated with a linear regression equation. First of all, the slope of the regression equation predicts the change in y given a unit increase in x. In economics, the slope is called marginal change. The y-intercept of the regression equation, that is the letter b, represents the predicted value of y when x is equal to 0. Sometimes it has meaning, and sometimes it just acts as an upper or lower bound on an expected value. So let's look at some linear regression equation examples from section 8.2 and 8.3 of our alternate textbook. We're going to assume that the correlation between the variables in these examples is significant. So in the first example, we're going to let X be the cost of a pair of Nike Air CB34 shoes in dollars at the Foot Locker, and we're going to let Y be the number of shoes that are sold at that price in 1 week. The linear regression equation that best goes through that data is given on the screen. So if the Foot Locker were to charge $150 for a pair of these shoes, how many would they expect to sell? Well, we can use the linear regression equation to make that prediction. We simply substitute the value x equal 150 into the equation. We turn the crank and we come up with an expectation that the Foot Locker could sell about 25 pairs of CB34s. Now, how do we interpret the slope in that equation? Well, the slope, -2.5, denotes the expected change in sales when the price is increased by $1. So for every increase of $1 in price, the Foot Locker can expect to sell 2.5 fewer pairs of shoes. Remember, this is an approximation. There's no such thing as 2.5 pairs of shoes, but because we're doing a calculation, that is a valid result in this case. How about the y-intercept? What does that represent? Well, the y-intercept of 400 represents the number of pairs the Foot Locker can expect to sell if the price was set at $0. While this would never happen, it does provide an upper limit on the number of shoes they could ever expect to sell. In our second example, let the explanatory variable x be the scores on test 2 and the response variable y be the scores on the final exam. Here I've shown on the screen the linear regression equation for the line of best fit that would go through the data points that we used to derive this equation. So in this case, if I scored a 78 on test 2, what would I expect to score on the final exam? Well, again, I would substitute the value x equals 78 into the equation, turn the crank, and I would come up with expecting to score 83 2/10 on the final exam. Now, what does the slope actually represent? Well, the slope of 4/10 denotes the expected change in final exam points when the test 2 score is increased by 1 point. So for every increase of 1 point on test 2, I can expect to score 4/10 more points on the final exam. What about the y-intercept? What does that represent? Well, the y-intercept of 52 represents what I could expect to score on the final if I scored a 0 on test 2. So let me close by making some comments about when we would use the regression equation. Keep in mind that the idea of regression is to make predictions about the response variable y for a given value of the explanatory value x. We call this predicted value y hat. You should only use the regression equation to make predictions when the correlation between the two variables is significant. If the correlation is significant, then in that case, you want to use the regression equation to predict a value of y for a given value of x, just as I've demonstrated in the previous two examples. If the correlation is not significant, in this case, we would not use the regression equation. Instead, you would use the average of all the y values from your data as the best prediction for any value of x. And I cannot emphasize enough that second one is very, very important to keep in mind when the correlation is not significant. And that concludes this presentation.